All right, now we're cooking with gas. Okay, so for those of us who weren't here, we talked about empirical formulas, which are the lowest whole number ratio. I posted the video from yesterday. We also talked about molecular formulas, and we talked about how we can find a molecular formula if we have the gram formula mass and we have the empirical formula. Example, let's say we have CH2O, and we say that this is 120 grams per mole. Okay? If we have the empirical formula, we know what we're looking for is 120 grams per mole, then we have to find out how many times bigger this 120 is than this. This weighs 30 grams per mole. One carbon, what's the matter, boys? Two hydrogens and one oxygen, 16 and 14, 30 grams per mole. We're looking for something that's 120 grams per mole, so this is going to be 4 times bigger than this. If it's 4 times bigger, instead of having one carbon, you're going to have 4 carbons. Instead of having 2 hydrogens, you're going to have 8 hydrogens. Where'd you leave it? Well, that's good news. And then oxygen, instead of having 1, you would have 4. So this would weigh 120 grams per mole and still have the same empirical formula as that. The empirical formula is the lowest whole number ratio. So let's say you have CH4. I'm going to call that times 1. That's the empirical. We could have C2H8, we can have C3H12, we can have C4H16. This would be times 2, times 3, times 4. There's only one empirical. The rest of them, including that first one, are also called molecular. Okay? So all of these are molecular, but the first one is empirical. That's kind of where we started yesterday. Then we said, all right, let's find the percent composition by mass. And we took, let's just do CH4 for fun. We know that this thing weighs 16. Okay, carbon, there's 1 times 12. And H, there's 4 times 1. That's 16 grams per mole. I don't know what's happening, but you need to stop. Okay? If I want the percent of carbon in the formula, we would take the formula, which is on the back of your reference tables, and we're going to say part, in this case, part of carbon, that's why I put a little C here, divided by the whole megillah, times 100. The part that's carbon was 12. That's this. The whole thing weighed 16. 12 divided by 16 is 75% carbon, which means there's 25% hydrogen. Remember that? Mm-hmm. Good? For those of you who weren't here yesterday, it's kind of like a little synopsis of what we did. Then we talked about finding the percent of water in a hydrate, which is going to lead us to what we're doing today and getting ready for the lab that I'm going to have you do. Okay? So if you have a percent of water in a hydrate, let's say we have a hydrate, we're going to just take any old hydrate like aluminum fluoride, and there's a little dot here, and I'm going to put 3 H2Os. That's a hydrate. And what I mean by hydrate is that there is a salt and it has water attached. Oh, I wrote H2O instead of water. Okay. This little dot right here means attached. So what I did yesterday is I drew it out and I said, all right, here's your salt. And you've got 3 water molecules attached to it. And if I want the percent of water in that, I would have to do exactly what I did here. But the whole thing is this. And the water is just those 3 water molecules. Okay? So let's find the percent of water in that. We've got aluminum, 1 times 27. Fluorine, 3 times 19. What's 3 times 19? You have calculators out? 57. Good job. Okay, that means that the aluminum fluoride is going to weigh 84 grams. So this part right here weighs 84 grams. And then I've got 3 waters. And each water weighs 18. So 3 times 18 is 54 grams. What does the whole thing weigh? 130? 138. 138 grams for the whole thing. And now we can just find the percent of water. So the percent of water is going to equal the part that's water over the whole thing. That's a bad W. Times 100. The part that's water is the 54 part. The whole thing weighed 138 times 100. And I have no idea what it is. I think it's 39% water. Good? Okay. Now, I don't know if we did this yesterday, so just bear with me. Keep this in mind. Did I say if we have a bucket? Did I do this? Yeah. Okay. And I put 100 grams of aluminum fluoride trihydrate in the bucket. How much of that stuff that's in the bucket is going to be water? 39%. So 39% of 100 gives you 39 grams, and then the rest is going to be the salt. Okay, so we're actually pretty good shape then. You have a question, or are you just being fabulous? No. Oh. I thought you went like this. Okay. No. Movie. Yeah, what movie should we watch? Pinocchio?
Let me actually watch Pinocchio.
We're not watching Pinocchio.
You should just watch like an episode of Jimmy Neutron. Wow. Neutron.
Okay, so now we're going to go from the percent to the empirical formula. This we have not done before. Okay? Well, you might want to take some notes. I am videoing, so if you need to go back and look at it later, you can. Okay? Let's say you are given a percent, like 75% of a substance is carbon and 25% of it is hydrogen. And I ask you to give me the empirical formula. So we did it the other way. I took the substance and I made it into, oh, look at that, that's the answer. That's the answer. And we made it into percents. But what happens if I want to take the percent and make it back into an empirical formula? Just why? Well, let's say you have a sample of a salt, which I'm going to give you, and I say to you, I want you to tell me what the mole ratio of the salt to the water is going to be. Like, how much water are you going to have if I give you this hydrated salt? Okay, so we'll start with this simple example, and then I'll show you the one that you're going to do in lab. If you have 75% carbon and 25% hydrogen, and you assume you have a 100-gram sample, we can also project that we have 75 grams of carbon and 25 grams of hydrogen. Okay. We are looking for these numbers down here, the X and the Y. We are looking for them because we want to find the empirical formula. Right, Pinocchio? Okay. Those numbers, the X and the Y, are moles. They're telling you how many groups of carbon and how many groups of hydrogen you have. And this is a mole ratio, X to Y. A lot of times they'll ask you what the mole ratio is. You just look X to Y. I change grams to moles? Think back. Gram formula mass. So we can find moles if we have grams and we divide it by gram formula mass. Here I have 75 grams. If I have 75 grams and I divide it by the gram formula mass of this carbon, which is 12 grams per mole, how many moles am I going to have?
You said 12?
Yep.
6
I'm not quick enough for Cordelia. Okay. I'm going to have 6.25 moles. This is 12 down here. Rob, do you know where that came from, that 12?
You know, I understand. I was just...
Let me move it up a little bit so my big fat head's not in the way. All right. And then 25 grams divided by, what's the gram formula mass for hydrogen? 1. This one I could actually do in my head. 25 divided by 1, 25 moles. So these numbers right here, this number and this number is this number and this number. So if I take C and I put 6.25 and I take H and I put 25, is that my empirical formula? No, because my empirical formula is the lowest whole number ratio. These are not whole number ratio. So the last thing we're going to do is we're going to take whatever the lowest number is here and divide both of them by that number. 6.25 divided by 6.25 is 1. 25 divided by 6.25 is 4. Now I have a 1 to 4 ratio, which is the empirical formula. I know, it's exciting, isn't it?
Does it always become a whole number like that?
Not always. But for the ones I'm going to give you right now, it will.
So you're going to give us word problems like this?
Okay. So the problem will be, you're going to get a compound, and I'm going to say it's such and such a percent of this and such a percent of that. What is the empirical formula? And you just have to remember that these numbers are moles. Let's try another one. Let's do 52.7% potassium and 47.3% chlorine. So there's my problem. I've got a sample, and I know that 52.7% of it is potassium and 47.3% is chlorine. How do I find the empirical formula?
Turn the percent to grams to moles.
Yep, 52.7 grams, 47.3 grams. Now we're going to do the mole formula. Moles equals grams over gram formula mass. We have grams, 52.7. The gram formula mass of potassium is 39. I have no idea what this number is. 52.7 divided by 39. 1.8? 1.4. 1.4. And then we're going to do the same thing over here. 47.3 grams divided by 35 grams per mole. I'm just changing grams to moles. And then we're going to end up with 1.4 moles of chlorine as well. This was potassium. So my ratio looks like this. K 1.4, Cl 1.4. And it's just KCl. Because I'm going to divide by the lowest one. They're the same this time. KCl. You want to see one that doesn't work out that nice? Okay. Let's do 70% iron and 30% chlorine. This is Cordelia's biggest nightmare right here. 70 grams divided by, what's the gram formula mass of iron? You find it? What'd you get?
1.2? I don't know. I'll have a calculator.
Why don't you have a calculator? They're hanging on the door.
I don't know.
1.25? moles of iron. And that you were on the right track, yes. 30 grams of chlorine divided by 35 grams per mole. .857. So I'm gonna keep it .857 just so that because this one comes out a couple decimal points. So that's moles. All right. So here's my ratio: Fe 1.25 and chlorine .857. Because when they are looking at samples of something, you need to be able to manipulate those samples to figure out how much of each thing you have. That's why.
Why do you need to know?
Because that's what the curriculum says you need to know.
You have less than 1 chlorine.
Well, let's divide both sides. So this one's going to be Fe. Something's not right here. Is this 2? And chlorine is 1? That's not right.
No.
Something's wrong.
What did you do, Miss?
No, I don't know. I didn't do anything. So 70 divided... Hold on a second. 70 divided by 56. Oh!
What, can you not round?
No, I wrote the wrong stupid thing down. What is this? 1.25. We'll just go with it. 1.25 divided by .857. It actually shows my point, but this wasn't the one I was doing. All right, so it's Fe 1.45 and then chlorine 1, right? All right, this number is not close enough to 1 or to 2 to round it. Yes. So what you're going to have to do to get rid of this is almost like 0.5, right? We're going to double everything to get rid of it. So this would become Fe3. 1.5 doubled is 3. Chlorine 2.
That's not 1,
I know, but it's 1. The 5 made this a 4, and this is... It's if you're in the middle, you're gonna double them. If you're close to something, you're gonna keep it that. Like if you're close to 1 or 2 or 3, then you keep it that. If you're in the middle, you have to double it to get rid of it at the end. Let's do the one that actually I was going to do before, and you'll see it again. 70% iron. What?
If it's like 0.9.
Yes, and then you just leave it. Let's do oxygen because that's the one I was actually supposed to be doing, but I'm a meatball. All right, 70 divided by 56. It's going to give me my moles, which we did here, which was 0.857. And oxygen was 30 divided by 16. And 1.875. Okay, now we've got Fe 0.857, and we got oxygen 1.875. Okay, we're going to divide through by the smallest number, 0.857. This is going to be Fe1, and this is going to be 1.5. What? I don't know. I am. Did I do this one right? I was just testing you.
Of course.
Isn't that what every teacher says?
We believe in this class.
Alright, let's fix this mess that I just made. Thank God I have you guys. Okay, so this is 1.25 and O is 1.875. Is that right now? Oh, phew, thank God I have you. Alright, let's divide by the lowest number, which is now 1.25. 1.25. 1.875 divided by 1.25. Aha!
You should put
Fe1, O1 and a half. You see how it came out as 1 1/2? That's a problem, isn't it? So what do we do to get rid of that half? Double it. So Fe2O3. Ooh, that was like the longest problem I ever messed up. I just keep going with the mess up. What's that? No, I didn't. Because I knew what the answer was, and I was focusing on the answer. I knew it was going to be 2 and a 3.
I said no.
Mm-hmm. What's the matter? All right, let's try another one. 32.4% sodium. 22.5% sulfur. And 45.1% oxygen. What's the empirical formula? I know what the answer is already, so I did it like 4 times today.
Oh my god. So why don't you just write it out? I just looked that one.
Nobody will know. They'll know. Nobody will know. They'll never know.
That's a little too much. You got scared. No, he wasn't expecting that. Right? Yeah, it's almost slow.
All right, so let's do some math and try not to mess it up. 32.4 divided by 23, 1.4. 22.5 divided by 32. Whoa. 0.7. And 45.1 divided by 16. 2.8. So here's my ratio. Na, 1.4. S, 0.7. O, 2.8. 0.7, 0.7, 0.7. This is going to be a 2. S is going to be 1. O is going to be 4. So Na2SO4 is your answer. Easy peasy?
Yeah. Just like divide over.
Okay. It's more than just dividing. It's understanding what I'm actually doing. I'm finding the mole ratio. Okay? Because now, the lab. Okay? I am going to hand you a hydrated salt. This hydrated salt has water attached to it. So you're going to get a salt. It's going to be a salt of copper 2 sulfate. And it's going to have water molecules attached to it. Okay? Your job is going to be to figure out how many water molecules are attached to it.
Oh, you have to like measure it?
Yes. So I'm going to hand you a sample, and this sample could be any size, but I'm going to pick 92 grams for my hydrated salt. That's how much my salt and my water weigh together. Then I'm going to ask you to dehydrate that salt. How do you think you're going to dehydrate it? Take the water out. How are you going to take the water out?
Boil it.
Right, you're going to heat it up. Okay, it's not going to boil. It's not going to look like boiling water because it's a solid salt. But if I start to heat it up, the water is going to vaporize, right? It's going to turn into a gas. And when it turns into a gas, that water is going to go into the atmosphere and go bye-bye. Okay, and then after you heated it up, where'd my numbers go? You're going to get an anhydrous salt. And let's say that anhydrous salt weighs 55.88 grams.
Are we gonna have to compare them?
What do you mean?
Like,
Yeah, you're going to have to weigh it.
oh.
You're going to get a random amount. It's not going to be 92. Yours is going to be anything from like 5 grams to 4 grams to 0.6 grams. It could be any amount. 55.8. Okay? So you're going to have 2 measurements in your lab. You're going to have the mass of the hydrated salt, and you're going to have the mass of the anhydrous salt.
Now
You're also going to have the mass of the dish, and you're going to have to subtract that too. But let's take one step at a time. Okay? So we have the hydrated salt, and we have the anhydrous salt. Nope, this is now work. Okay? Your brain's engaged. If you have the mass of the hydrated salt, which, if you think about it, is just salt and water, and you have the anhydrous salt, which is only salt, can you find the amount of water that evaporated? What do you do with those numbers? Subtract those suckers. So how much water did I lose when I heated this salt up? No. I don't know. 36.12? Okay. If that's the case, what percent of my sample was water? No, not 36%. What percent was water? No, it's not 64. Shouldn't be 64. 36.12 divided by. No. What's the formula for percent? Part that's water over whole times 100. What part is the water? 36.12, right? And what's the whole thing weigh? 92. So what's the percent that's water? 39.3% water. Okay? Wow. Okay. Now, what should the percent of water be in copper 2 sulfate? Do you remember? No, it's 36%. I'm just looking for it. Right here. 36%. It should be 36%. What's the percent error? We got 39. How do you do percent error? Okay. Percent error is going to equal the measured value minus the accepted value over the accepted times 100. And we're going to take the absolute value of that. What was my measured value? 39.3. What's the accepted value? What should you have? 36 divided by 36 times 100. So what's the percent error? 39.3 minus 36 divided by 36. I'm going with 9% error. Okay? You with me? No, you guys are still on vacation mode. Come back. Come back. If I have to be here, you have to be here.
When you get paid and we will. It's different. That's what I said yesterday.
You're going to get paid eventually. You just have to learn enough to get paid for it.
No, just not for this stuff.
Yeah, well, we know how Cordelia feels about chemistry. Okay? Any questions on this stuff? You could do percents. You could do mole ratios and find the empirical formula. You sure? Okay. So if you have percents that you calculate in lab, would you be able to find the amount of water in your substance? It's like a period and a half lab. No, we're not doing the lab today. I got to get the